Okay, hello everyone. It is time for our third lecture, and it is still about first order differential equations. And today we will end chapter 1 by the following theorem. So here is a theorem in chapter 1, still in chapter 1, 1.2, I think. So here is a theorem. And this theorem I will call it, or it is called existence and uniqueness. Existence and uniqueness for first order differential equations. Okay, what is this theorem? It says if you start with an initial value problem, suppose that you have initial value problem. This initial value problem is just a differential equation, dy over dx equal f of x and y. And you need, so this is a differential equation, right? And you need an initial condition here. Y of x0 equal y0. Yeah, this is initial condition. So together, we call them initial value problem. Now, if f and partial f partial y, so the derivative of the right hand side with respect to the dependent variable are continuous in a rectangular area, including x0, y0, then the initial value problem will have a unique solution in some interval I, including, so this is an interval, yeah, including x0, yeah. So what the new thing is a rectangular area. So we need f, this function, to be continuous on x and continuous on y, continuous on both variables, and we need its partial derivative with respect to the dependent variable. This is dependent, yeah, with respect to the dependent variable. Also, this thing could have both x and y. It should be continuous on x and continuous on y. And in a rectangular area means x can be squeezed between a and b, and y can be squeezed between c and d, yeah. And then if you go and draw this in the xy plane, just to give you an idea, xy, so x between a and b, yeah, and here between c and d, yeah. If you go and draw this thing, then you're gonna have something like this. So you're gonna have that area, right? So this is a rectangular area, means x is squeezed between two numbers and y is squeezed between two numbers. This is the rectangular area, and it should include that x0 should be between a and b. So say x0 is here, yeah? So this is x0, and say y0 is somewhere here, yeah, y0, then x0, y0 is here. So that point here is x0, y0, and should be in that rectangle. Then if everything is okay and your function is continuous here and its partial derivative is continuous here, initial value x0, y0 is inside that rectangle, then for sure solution exists and solution will be unique. So there is no problem to ask a question and asking you to find the solution when I guarantee for you that f is satisfying the two conditions. I'm calling it them two conditions because there's a condition on f and condition on the partial derivative of f with respect to y. Now, let me show you why do we need to know such theorem. So if you go to any of the questions that I give you before or the questions that I will give you later, you will surprised by given interval with the question. For example, if you go for question, let me go with that question. I think it is the second last question that I give to you. So it was that thing when I say, I don't remember the question, but it is the second last question. It was saying show that xy cube minus xy cube sine x equal 1 is a solution for. And if you remember the differential equation dy over dx here, maybe I forgot to write that there is a condition here, cosine x plus sine x minus 1 times y. And here we have 3 and x minus x sine x. And it says on the interval, 0 to pi over 2. So I'm surprised about this interval. Is this interval for x or for y? So this interval always is given for the independent variable. So this is for the independent variable. So it is for x. Yeah. So why we need this interval? Why the question is give you an interval with your differential equation? So there should be a reason behind this interval. Now I'm going to show you why solution for such thing exists. Now I'm going to ask why solution exists for this differential equation before doing anything. So from now on, if I give you a question, I give you an interval, then there is a reason behind this. It should be related to the existence uniqueness theorem. So here is the function, your function here, f of x and y. I want to apply now, if I applying existence uniqueness theorem. Now there is f of x and y. Yeah, what is that? It is x cosine x plus sine x minus 1 times y over 3x minus x sine x. Now, is this continuous on x? And is this continuous on y? Let me study this. So it is on y, it is a linear function, so it is continuous, on y. Why? Because this is just a constant. This thing in y is a constant. It is. You can look at this like 3 times y. So because it is linear, because it is a polynomial in y. Yeah. Now, why it is continuous in x? Is it continuous? So when I say continuous on y or in y, continuous in y, so over which interval? Minus infinity, infinity, when y is between minus infinity and infinity. So we have no condition on y, right? it is always continuous in y. Now, is it continuous in x? So in x, it is a quotient function. So to be continuous in x, it should the denominator should not equal to 0. So I'm gonna say continuous in x if denominator is not 0, if or when x minus x sine x is not 0. So I have to exclude here. So let me just show you what's going on here. Now, back to that function here, which is, to that equation. What if x sine x equals 0? Then this implies that x times 1 minus sine x should be 0. Then either x equals 0 or x should be pi over 2, sine x equal 1, which means x equal pi over 2. Yeah? So for x, you have the following. So for x, you have the 0 here, it is a problem, and here it is a problem at pi over 2. So here discontinuous, yeah, and here discontinuous, right? Discontinuous, yeah. So we have 3 intervals for where you can work with that differential equation and your function will be okay. So we are good here, bad at that point, we are good there, we are good there. So for x now, for x, so continuous. So let me go with x. X, if x is less than 0, which means minus infinity to 0 is okay. And 0, so x between 0 and pi over 2 is also okay. And x bigger than pi over 2, less than infinity is okay. So this is this one is okay, this one is okay, and this one is okay. So when I give you the differential equation, I should give you one of these intervals in the question to guarantee that this function is satisfying the existence uniqueness theorem. So in the question, he decided to give you that one. But either one of the 3 is okay if there is no initial condition. If there is an initial condition, then you need to choose the right interval that includes x0, which is the initial value for x. So since we don't have initial value for x, then it is okay to choose any of the 3. He decided to choose the middle one. So the function now we know why he is giving an interval in the question to guarantee that that differential equation will have a solution. Now, if you want to continue with checking the uniqueness and existence theorem, I'm gonna show you how to do the partial f, partial y. Now when you do partial f, partial y, you know that thing. So let me go with f first. F here, it is something here, yeah, times y, right? Everything here in x. Now when you differentiate, then that thing is constant, so y is changing, but x is a constant. Then when you differentiate, you get that thing, right? So you get that thing, which is, I'm going to go with that function, which is x cosine x, let me see, x cosine x, yes, cosine x, and then plus sine x minus 1, okay, you get this, and you get here 3 and x minus x sine x. So this is the derivative, and again, if you study now, this is constant in y, so constant in y, in y. So constant function in y, then always differential, so always continuous. So always continuous, which means when I say continuous in y, this means that continuous on the interval, which interval now? It is minus infinity, infinity for y, right? And now if you want to study for x, is it continuous in x? Again, for the continuity of this, df over dy, continuous in x, again when the denominator is not equal to 0, when x is belonging to one of the three intervals, and he decided to go with this interval. Yeah, so this is his choice, but any of the three intervals is okay. Now we know from now on why he is giving us an interval when he give you a differential equation to solve or to verify that a given function is a solution for it. So by doing this, I can say now that my differential equation has a solution in the interval when x between 0 and pi over 2. Yeah? So it has a unique solution in 0. So I cannot say a unique solution now because it is not an initial value problem. If x0 and y0 are given, then I can say it is a unique solution. If there is no initial condition, then there is a constant of integration, and you're going to have a general solution, which is solution exists but maybe not unique. So there is a family of solutions. Now let me go now and do for example, here is I give you another example. If you have I think it is an example from the book also. So you have dy over dx, and here you have minus 1 over 2y. Yeah, and in this, I don't remember which question is this, and we have the solution where the solution has the solution, let's say y squared plus x minus 3 equals 0 for x belonging to minus infinity to 3. Yeah. So why this differential equation has a solution when x between minus infinity and 3, and this is the solution. So why we need that condition here? If I say verify that this is a solution for this, I have to give you that interval. Why in this interval there is a unique solution for this differential equation? Again, if you look at that function as a function of x and y, fortunately we don't have an x, so nothing to check for x. Now if you go here and just here solution, if you applying existence uniqueness theorem. Yeah, so f is always continuous. F is continuous in x. It is a constant, right? Constant in x, always continuous in x over the interval minus infinity, infinity for x, right? We don't have any problem in this. Now if you go for y, f is continuous in y over the interval. Which interval you're going to choose? There is a problem at y equals 0, so you are good here. So this is 0, because 0 here makes the function discontinuous in y. So I'm studying y now. So here here is good, here is good, here is bad. So we have to choose either minus infinity to 0 or 0 to infinity. So both are good. So minus infinity 0 is good, and 0 to infinity is good. Yeah, this is good and that is good, but at 0 it is not good. Now what should I do in this case? What should I do in this case? Now this interval is given for x, it is different from this one, but this one is y, this y is living here, right? Now what if x equals 0? Now let me go here, and if y is 0, now if y equals 0, then you're gonna have the solution will be 0 squared plus x minus 3 equals 0. This means x equals 3, right? Yeah, this means x equals 3. But if x equals 3, then y equals 0, right? If x equals 3, then y should equal 0. And when y is 0, it is discontinuous. So there is, at x equals 3, there is a problem now. I'm good here for x, and I'm good here, but I'm bad at 3. Then it is your choice whether to choose that one or that one. Now, if you want to decide which one to choose, you need initial condition. For example, if he is saying y at 0 equal 1, then you are forced to choose this one because 0 belongs to minus infinity 3, right? But we don't have this one, so any of them are okay, and he decided to go with minus infinity 3. Now for this one, I didn't check the full thing because the next thing is to find the partial derivative. When you do the partial derivative for this, you get, I think you get 1 over 2y squared. And again, you're going to have a problem at y equals 0. And again, you will have a problem at x equals 3. Yeah? If you want to just here check, if you want a partial f partial y, then you get 1 over 2y squared. And again, the problem at y equals 0, and which leads to a problem at x equals 3. Then you have to choose between minus infinity 3 or 3 up to infinity. So this just gives you some reasoning why he is including always an interval with any differential, with some differential equations, because your function f or its partial derivative may have a problem. Now the next thing, so let me now go with the next thing. The next thing is to go to chapter 2 and start now here. So in chapter 2, so we will know here, we'll study how to find solutions for the first order. So these are only for first order. Chapter 2 is just for first order differential equations. Yeah. So all the sections here are giving us. So it is giving us techniques to solve first order DE, yeah, differential equations. Now the first technique, section 2.2, I'm going with the first technique. First technique here is called separation of variable technique. Yeah, so you have here, let me start with a first order differential equation. So this is a first order differential equation, dy over dx equal f of x and y. This thing is a first order differential equation, yeah? And this is called on general form, form. Yeah, general form. So this is the general form for first order. Now this technique here, separation of variable, it means that your f, we're gonna have more than one variable and you need to separate them, right? So you need to separate them. So you have only first derivative here, and every expression in x and y is on the right hand side. Now I'm gonna just, before starting, what if we don't have y here? What if fxy has no y? If you have no y, let me give you an example. If I say find the general solution, so GS, general solution for this dy over dx equals sine x, yeah? So you have no y here, so it is like calculus 1. If you know the derivative, can you give me the function? So you started with to get that derivative. Now this is very easy, so it is just how you undo the derivative. So when I say find the general solution, this means undo the derivative. Undo the derivative. And get y. And get... I'm saying y because y here is the dependent variable. Yeah? Now it is very easy here. This is the solution here. Solution. Very easy. You have dy over dx equal sine x. Yeah? Now all what you have to do is integrate both sides. And here is dx and here is dx. Right? And now this with that cancel. Yeah? And now when you integrate dy, you get y. And always when you do indefinite integral, you add a constant, right? You add a constant. And when you integrate this, you get minus cosine x, right? And another constant. So I need to differentiate between them. So I'm saying C1 and C2. Now, you solve now for y. Solve for y, then y will equal to minus cosine x. And then I'm subtracting C1 from both sides. Yeah? And then I'm getting plus C2 minus C1, right? Now, this is a constant minus a constant, then you will get a constant. So no need to call it C2 minus C1 because it is a constant. So y is finally y equal minus cosine x plus c. So you get your y, the dependent variable here. Then this is the general solution for the differential equation. Which differential equation? Here is the differential equation. So that thing is a solution or a general solution for our differential equation. This is a very simple case. Now, the question is, will you add a constant c to both sides of the to the y side and the x side? I'm gonna say from now on, remark. From now on, add c to x side only. Yeah, because if you add to the y side and the x side, then you need to collect them in the x side to solve for y, and then you get two constants, the difference between them, you call it c. Now, let me go now, what if your function, now we said if the function has only x, but if the function fxy, that function, has still x and y, but the good thing about this thing is f of x times, so let me call it g of x times h of y. Yeah? This means that your function is a product of two functions, one of them completely in x and the second one is completely in y. Now, in this case, if you have this case, so of course, or division is okay also, right? Because always multiplication and division is one thing, right? Now, what you're gonna do if you have this case, then we call the differential equation. So of course you have here dy over dx, right? Then dy over dx is a function completely in x only. So here x only, and here you have y only, right? Y only. If you have this thing, then we call the differential equation is separable. Separable means you can isolate the x in one side, which is the right hand side, and isolate the y's in the other side of the equation, and then you can integrate. So I'm going to show you what is going on here. So you know, always if you want to solve a differential equation, you need to undo the derivative. Now, can I undo the derivative here? Yes, I can undo the derivative here. But can I integrate g of x and times h of y with respect to x? No, there is no matching between. Suppose that you put dx here and you put an integral here. What's going to happen? So there is no matching. So here is a matching, but y and x, there is no matching. Then you need to isolate the y in one side and the x in one side before integrating. So I'm going to say here steps to solve. If separable. So step number one, you isolate the y. So you separate dy. So here you separate the variables in the following form. So you're going to have dy here, and here you're going to have only y, and in this side you're going to have dx and then only x. So this is what you're going to do. So you need to separate all the y's with dy and all only x's dx. And the next step, number two, integrate both sides. And then add c to x side. Then the last step, if possible, then what you're gonna do, solve for y if you wanna. So in this way you get implicit solution, right? If you do step number two, you may get implicit solution. So this may give me implicit solution. Mostly implicit solution. For this reason, you need step number three here. Solve for y if possible. So you get y in this side, the other end, so everything else here. Solve for y, yeah, y equal. This means y equal to get explicit solution when possible. Yeah, and I can put here number 4. If there is when you have initial condition, find C. Yeah. So let me solve one question for you, or two questions. I will give you a hard one. So, because the technique is very easy, so let me go not with a hard one. I mean, that's so not very simple. It is something which is not very simple. So, okay, no, this is simple. This is simple. I go maybe. This is a question from the book. I don't remember which question. Solve the differential equation. So it is a question from the textbook section 2.2 that is solve the differential equation dy over dx equals secant square y over 1 plus x squared. Now if you look at this thing, look at the equation that he is asking us to solve. It is clear that this thing is just secant square y times 1 over 1 plus x squared. Or if you like, they are the division of two functions, one completely in y. So we have here only y, and here we have only x, right? So this, we call it separable differential equation. Now how are we going to proceed with this? All what you need is write every y in one side. So I'm going to just here go to that one, that equation. Yeah, I'm going to just maybe keep this in this side. I will multiply it with dx, yeah, so that I bring dx here. And also I multiply or divide both sides by secant square. Yeah. What will happen in this case if you multiply by dx? So here, if you have a dx, then that dx will cancel that one in this side, but dx will be here. And when you divide by secant square y, then secant square will cancel with that one, and you will get 1 over secant square. So I'm getting something here, solution. I'm getting something like 1 over secant square y dy equal to dx divided by 1 plus x squared, right? Now here everything in y and dy, everything in x and dx, right? All what you need now, after you separate the variables, the y is in the right hand, the left hand side, and the x is in the right hand side, integrate both sides. Now this thing, I don't know how to integrate this, but if you look at that thing here, 1 over secant square, it is cosine square y, right? Now this thing is, you go to the tables in calculus 2, this is just tan inverse x, right? And then you need to add a constant here, constant of integration. You don't need to add anything. Now when you have cosine square, this you can use an identity. So there is an identity says cosine square y is just half and then 1 plus cosine 2y, right? Now I'm going to use this, get rid of the square by doubling the angle, right? So you're going to have half 1 plus cosine 2y, and then here this thing need to be integrated. Now this half, I can take it outside, and I'm going to have that half outside, and then I integrate this with respect to y, right? Now then you're going to get half outside, and you get y here, and when you integrate this, you can use substitution here, but I prefer to go very fast. The integral of cosine is sine. And because of some substitution, you need to divide by the angle. So you need to divide by that 2. That 2 you divide by that 2. And then this thing is tan inverse x plus c. Now I ask myself, can I simplify this thing? The only thing that I can simplify, if you like, and I can multiply by 2, right? If you multiply the total thing by 2, then you're going to have 2c. So let's call this c1. So you get 2c1, and then you call it c, right? And here you get 2 tan inverse x, and in this side you're going to have you're gonna have now the 2 times, so I'm multiplying by 2, right? This 2 cancel that 2, and you will get y plus sine 2y divided by 2, right? 2y half here, and then plus. Now, can I solve for y? It's very hard to solve for y. Then I can stop here and say, hey, I got an implicit general solution. So I got here implicit general solution, because I cannot make it or solve it for y. It's hard to solve for y. Hard to solve for y. Now let me proceed with another question here. Another question just to show you that things are not always very easy. I can give you something which needs some steps before doing the separation. So here is, I give you something like, what will you do if you have dy over dx equal to 2yx minus x? Now, is this separable? Is this the product of two functions completely in x and completely in y? It is not, because here it is x and y and it is multiplication, but we have that thing which is make it not separable. But be careful, sometimes if you take a common factor, now it is separable. So here it is separable. So separable. Now, because you're gonna have something in x completely, something in y completely. So I gotta tell you here as a remark, sometimes you may need to take a common factor to make it separable. So this is the common factor. I'm taking x as a common factor. So let me give you another question now. So maybe a harder one. Okay, what is the second question that we're going to solve? It says solve the initial value problem now. Here, solve the initial value problem. Again, I'm taking a question from the book. Initial value problem. In this case, I'm giving you x squared dy over, let me write it down here. X squared dy over dx equal to 4x squared minus x minus 2 divided by x minus 1 and y plus 1. And he's saying here you have y of 1 equal 1. Look here, what is the difference now? I'm calling it initial value problem. We have initial condition here, then this means use this to find the constant of integration c. How are you going to solve this? Is this separable? Now let me look here. First step, I will need to write it on the general form. So if you divide by x squared, then you're going to have here solution. It is clear that you're going to have dy over dx equal to, I'm going to write it 4x squared minus x minus 2. And I have the x squared, that x squared coming down here. And I like to keep this alone here, alone as 1 over y plus 1. Now, look, this is completely in x, this is completely in y, right? So this is a product, and this means that it is separable. Yes, it is separable. Now what is the next step? I need the dx to be here and I need the y plus 1 to be here. Then my next step will be, hey, why you don't multiply by dx and also multiply by also y plus 1. Yeah? When you do this, you get here, you get what? You get y plus 1 dy, and on the other side you are getting this 4x squared minus x minus 2 over x squared x minus 1. Now it is time for integrating, so and the dx of course. Now it is time for integrating. Now put the integral here and think. Now for this one I don't have any problem, so I have y squared plus y over 2 here. So we have y squared over 2 plus y, yeah? And the other side, this is very complicated, so the degree of the numerator is bigger than the degree of the denominator. In this case, you need partial fraction, so you need partial fraction. Let me explain to you the partial fraction, so you don't have any problem here, you need just to integrate that thing. So how you do the integration for that thing? So let me just say I'm gonna do it here. So I'm gonna have 4x squared minus x minus 2 divided by x squared times x minus 1, and you know you're gonna have a over x. I need from you to go to calculus 2 and review partial fractions. So it is a constant over x plus a constant over x squared plus a constant over x minus 1, c over x minus 1, right? And now the next step is to go and multiply everything with what? Well, x squared and x minus 1, right? Finally, you're gonna get what? Finally, you will get the following. You will get 4x squared minus x minus 2 equal to a times, so 1x, so you're going to have x minus 1, yeah? And you're going to have b times x minus 1, and then you get c times x squared, right? Now one by one, take x equals 0 now, a value, this is true for each x. Now take x equals 0, then this side will be minus 2, this side will be minus b. So you get 0 minus b plus 0, then your b will be 2, right? And now continue in this way, take another value for x. Of course you can do it by comparing powers, comparing the coefficients of the polynomials. Yeah, you can compare the coefficients of polynomials, but I prefer to go and plug the values for x because this is true for any value of x. Now take an x value, another value, take x equal 1, I'm choosing x equal 1. Now what you're going to have here, this side will be 4 minus 1 minus 2 equal 0, 0, 0 plus 0 plus c, right? Then c will be 1. Now try another value because you are out of good values here, so try x equal 2 for example. Then here you get 16 minus 2 equal to 2a, yeah, plus b, and then plus 4c, right? Now plug in the value for c, so 4 times 1, and b is 2, and here is 2a, and here you get 12, and then 2a will be 6, and then a will be 3, yeah? So you got a, b, and c. Now we have that integral, so we got the y squared over 2, yeah, and plus y, and that integral now become a nice integral. This integral will be the following, yeah? It will be 3 over x plus b is 2 over I think 2 over or minus 2. I'm not sure if b is 2 or minus 2, so it is it depends on that polynomial. I think it is minus 2 or 2, sorry, 2 or minus 2, I'm not sure, but it says 2 here, maybe I'm wrong. 2 over x squared, and then plus 3 over x plus 1, and then dx. Yeah, now it is a nicer, so you just cut that big fraction into 3 small fractions. Yeah, and then if you want to integrate 3 over x, then 3 ln absolute value of x. And if you want to integrate this, just imagine what is this thing. So this thing is just 2x minus 2, right? Now you go with power rule. Power rule says you have 2 and x power minus 2 plus 1 over minus 2 plus 1, right? And here you get 3 and ln absolute value of x plus 1 and plus c, right? So it is almost, we are almost there, So now this thing is just 3 ln absolute value of x, and here we have minus 1, so minus 2 over x, right? 2 over x. And the last thing is 3 ln absolute value of x plus 1 plus c. This is y squared over 2 plus y. This thing is implicit solution, implicit general solution for differential equation, the differential equation, right? Now, since he is giving you a value for the initial condition, so he's saying y of 1 is 1, then it's clear when you plug 1 for x, you get 1 for y. So you get 1 over 2 plus 1 equal to 3. And ln of 0, ln of 1 is 0, right? 0. And then here minus 2 over 1, and here plus 3 ln of 2, right? Plus c, right? Now finally what we got here, if you want to calculate, so 3 over 2 equal to minus 2 plus 3 ln 2 plus c. Now you need c. Very easy. Just rearrange things. Solve for c now. Now we need to solve for c. Clear c will be 3 over 2 minus 2, and then plus minus 3 ln 2. Yeah, and then that's it. So if you want to combine these, this is 2, which is 4 over 2, 7 over 2 minus 3 ln 2, right? Now this is just the constant c, the constant of integration. No need to go and do it using calculator, so we can keep it like this and say that my solution here is 3 ln absolute value of x minus 2 over x plus 3 ln x plus 1, and then the c is just 7 over 2 minus 3 ln of 2. This is solution for the initial value problem. So the differential equation plus the initial condition. So this is a particular solution. Yeah. By this, we reach the end of the section separation of variables. I hope that you enjoyed this lecture, and I wish you the best, and see you in the next lecture.